So now, there are special cases involved with integration by substitution, none of which are fun. Um, these are special cases that you would not be expected to see without see the first time without some type of guidance from someone who has more experience. So this is me exposing you to these. Basically, we always kind of pray that these are not ones that we ever see again. And there's three special cases. One involving an integral that results in an inverse tangent. Second is completing the square, and the third involves long division. So, first one, the case that involves inverse tangent. When I look at the integral of 1 over x squared plus 64, I don't know of anything that has that as its derivative off the top of my head. So substitution. Well, if I say that u is equal to x squared plus 64, or even just the x squared, I end up with a 2x and a derivative that's not going to cancel out when I replace the dx. So it's not that. This is one where it's set up that I have a constant divided by the sum of perfect squares. So x squared plus 64, 1 is a constant on top, x squared plus 64 is a sum of perfect squares. And what we are really trying to do is we're trying to change this because the derivative of inverse tangent is 1 over x squared plus 1. And we want to get it to something that looks like what I wrote in green. So the way this works is this x squared plus 64 is x is being squared and 8 is being squared. So my u is going to be the quotient of what is being squared. And this doesn't look very helpful to me. So du dx is equal to 1/8. So dx is equal to 8 du. Because I look at it and go, there's no x over 8 for me to replace with u. But if I rearrange and I solve this for x, 8u is equal to x. And now I can replace the x. So I have the integral of 1 over 8u squared plus the 8 squared times 8 du, which is the integral of 8 over 64u squared plus 64 du. I can pull an 8 out on the top. I can pull a 64 out on the bottom. And I now have something that looks like the inverse tangent derivative. So I have 8 over 64 times the inverse tangent of u plus c. So I have 8 over 64 times the inverse tangent of x over 8 plus c. And there is our antiderivative. Again, you would not have been expected to recognize to do that on your own without it being shown to you first. That's how I learned it, is somebody had to show me how to approach this. With special case number 2, this is when I have something where I have a fraction and the degree of the numerator is greater than or equal to the degree of the denominator. Because of the fact that, especially with power rule, our degree should always go down. When I take if I say the denominator is going to be my u, well then I would lower its degree by 1 to have a derivative that should cancel out. So I need to get it to a place where the degree of the numerator is less than the degree of the denominator. So what this goes back to is the idea of long division. Like if I were saying I want to do 7 divided into 512. Well, I would say 7 doesn't go into 5, so I'd look at 51. 7 goes into 51 7 times. There's 49. So 7 times 7 is 49. Subtract that, leaving me with a 2. This 2 comes down. 7 goes into 22 3 times. 3 times 7 is 21. Subtract that. I'm left with 1. There's nothing else to bring down. So I would write this as a 1 over what I'm dividing by. So I have 73 and 1/7. The same thing happens when I'm doing long division with algebra. It just looks messier. I look at the first term. What would I need to multiply x by to get x squared? Well, x. X times x minus 1 gives me x squared minus x. But I'm subtracting that. So the x squareds cancel. 2x minus a negative x becomes 2x plus x, which is 3x. What would I multiply x by to get 3x? Well, I'd multiply by a positive 3. 3 times x minus 1 gives me 3x minus 3. But I'm subtracting that. So the 3x's cancel. Nothing minus a negative 3 is a positive 3. There's nothing else to pull down. So I will have plus 3 over the x minus 1. So this integral is the same as the integral of x plus 3 plus 3 over x minus 1. Well, the x, I know its antiderivative is 1/2 x squared. The antiderivative of 3 is 3x. But then I have the integral of 3 over x minus 1 to worry about. I don't know anything that has that as its derivative. So I'm going to say u is equal to x minus 1. du dx is equal to 1, so dx equals du. So just this part gives me the integral of 3 over u du, which is 3 times the natural log of the absolute value of u plus c, which is 3 times the natural log of the absolute value of x minus 1, because I need to make sure that x minus 1 is positive to take the natural log. So that means that all my original integral then, all of this is equal to the 1/2 x squared plus 3x plus 3 times the natural log of the absolute value of x minus 1 plus c. And that's just a case of you probably haven't really done any long division since Algebra 2, so it's been a while. The third special case is completing the square. This is also one of those where it's been a while. If I look at the integral of 1 over x squared minus 2x plus 2, this is similar to like our special case number 1. I would love it if this were the sum of two squares. Well, if it's the sum of two squares, in order to be the sum of two squares, I would need to complete the square. So to complete the square, I have x squared minus 2x plus something, and then the plus 2, minus something. The first blank is for what would add to complete this and make it a perfect square. The minus the blank is going to be the same number, but to keep things balanced so I don't end up with a different expression. It's an equivalent expression. So I'm going to take the negative 2. I want to divide that by 2 and square it. And that's going here. But I put the same thing here. So all of this is that I have x squared minus 2x plus 1 is x minus 1 squared, plus 2 minus 1 is 1. So this is the integral of 1 over x minus 1 squared plus 1 dx. I don't know anything that has that as its derivative, so u, I'm going to say, is equal to the x minus 1. Du dx is equal to 1, so dx equals du. So I have the integral of 1 over u squared plus 1 du. That I do know is inverse tangent of u plus c, which is the inverse tangent of x minus 1 plus c. Again, with these three special cases, they're hard. They're challenging. I should say they're hard. They're challenging. They're tough to notice. Fortunately, they are rare. They don't happen very often.